Well, me too, I would like to take this opportunity to thank the organizers for the invitation and, of course, for the wonderful job they've been doing. It's been a really great conference so I'll talk a little bit about the experiments we're doing in Paris on the Casimir-Polder interactions. I'll mostly talk about the experiments we've been doing for many years with atoms, mostly focusing on measuring the thermal effects of the Casimir-Polder interaction. If I have time in the end, I would like to sort of give you a sort of preview of these new experiments we're planning with molecules, which we're very excited about, but it will kind of depend on time. Let me just start very quickly here. Let me just show the same slide as pretty much everyone else. The sort of atom surface interaction is a sort of dipole type of dipole-induced type here kind of attraction. It's a 1 over Z3 if the atom is close to the wall. And here I'd just like to define the image coefficient epsilon minus 1, epsilon plus 1 if this thing is not a perfect conductor, which I'll be using a lot throughout the talk. In principle, it's attractive, but I guess you all know these things. What I just want to say here is that it causes an energy shift to the atomic levels, and this is what I'll be measuring. I will not be measuring forces, unlike you call it measure Casimir forces. I'll be measuring shifts. And in order to do that, I have to remind you that these shifts are different for every excited state and depend on the sum of all the allowed couplings in every state. And at the end, I get a sort of 1 over Z3, C3 over Z3 law. And this C3 coefficient here depends on the actual excited state I'm probing and on the dielectric properties, in particular this image coefficient of the actual surface that I have in front of me. All right. So I guess you know the description of quantum fluctuations and that there are effects of retardation, so I don't have to go through that again. Just to mention some numbers here, like for the atoms I'm looking at, which are mostly alkali atoms, sort of retardation effects start to come into play after 100 nanometers, and they're not very important in my case. What I would like to spend a little bit more talking about is temperature effects. Well, because my talk is temperature, right? So in essence, all right, what you have is a sort of much bara sum that we've seen many times before. It's kind of interesting to sort of say that the effects of temperature, well, in the case of atoms, are not very big, which is a bit of surprising for me in any case. It turns out that they are big if you go very far away from the surface at distances that are greater than what we call the thermal wavelength, which in room temperature is about 7 microns. So at this regime, the interaction is linear with temperature, which is very good if you want to measure temperature effects. But actually it's very bad because the interaction at this sort of distance away from the surface is actually very, very small. You need something very accurate in order to measure it. These sort of accurate experiments, very nice experiments, were done in the group of Eric Cornell. But even in this case, like thermal effects were not demonstrated in the case of thermal equilibrium because this formula stands in thermal equilibrium. And they were actually demonstrated out of thermal equilibrium situation where you actually have a quadratic effect that we actually heard about a little bit yesterday. So this is the work done, experimental work on temperature, I would say. I like to focus more on what happens when you go much closer to the surface. So this is the sort of regime that I'm interested in. And, well, just a few words trying to convince you why this is important and what happens there. Essentially, well, the paradigm of sort of thermal radiation is a black body. If you want to calculate its spectrum, you just have to take the density of states, you have to multiply it by the Bose factor, by the energy of every mode, and then you have the sort of energy density, the black body flags below and so on. In reality, real materials are different, like they have a dielectric constant, and they like to absorb in certain frequencies, and they don't like to emit in all frequencies. But more importantly, what they do have is they have some certain frequencies dielectrics that they sort of support evanescent polariton modes, evanescent surface waves. And those surface waves, they have the right to be excited by temperature, so they have they take their population by the same Bose factor as all the other modes. It's a little bit difficult to count the density of evanescent modes, but this was done in, well, my knowledge, in a very nice paper by Jean-Jacques Creffet and some of his colleagues, of course. And what he found is that the density of evanescent modes depends on 1 over Z3, which is a sort of typical distance dependence. So they get more and more as you go closer and closer to the surface. And they also depend on the imaginary part of this image coefficient, epsilon minus 1, epsilon plus 1, which for dielectrics is actually a bell-shaped curve around the polariton frequency. So if you actually calculate the thermal emission from this surface, and this is actually done, I borrowed this graph from this paper, again, from Jean-Jacques Creffet, you'll see this, in this case you have silicon carbide. You'll see that if you go far away, you have a very broad spectrum, like around 1,000 microns away. And this sort of is still broad 2 microns away, but if you go very, very close, it's the evanescent modes that carry most of the weight. And the thermal field, which this is now a thermal field, becomes almost monochrome. I guess maybe you know about all this already. It's a sort of field of near-field thermal emission, near-field heat transfer, and all these things. What I'm interested in is what are the effects on atoms, because I'm working on Casimir-Polder. So I want to see what happens to the atoms when they're very close to the surface, and they feel the presence of these evanescent modes. And I'll just give a very hand-wavy explanation here. Maybe you won't like it, but well, you can complain afterwards. So what happens here essentially is you have an interaction of the atom with a sort of kind of radiation field at the frequency omega s, which is the surface wave frequency. And if you have an atomic transition frequency, omega 0, if this field is redly tuned, then the thermal field, which is evanescent, then the atom will kind of want to be sucked towards the surface. It's a sort of high field seeking sort of atom. Whereas if this sort of polariton frequency is bluely tuned, then the atom would like to be repelled away from the surface. And this would manifest itself in a sense as a sort of reduction of the C3 coefficient, which could go down to 0 or even become negative as a function of temperature, as I keep on increasing sort of excitation of the evanescent modes. Also, as an atomic physicist, I know that if you have a radiation that's kind of close to the atomic frequency, and just to remind you here that, you know, these sort of surface excitations have very low Q factors compared to atomic sort of frequency standards. Atoms can also absorb some of this excitation and gain energy due to this sort of to the existence of the surface, the excitation of the surface. This is kind of a surface-induced heating, some people call it, I think, but I'm interested in. So these are kind of the effects that I want to see. I want to see the effects on the shift, and maybe on radiative properties of the atoms, or sort of, I guess would be the equivalent of heating the atoms in the near field. Okay, I guess if you don't like this description, then you can actually do the perturbation theory. The evanescent modes are in there. You get the Matsubarel sum and the resonant term that we heard so much about yesterday. So this has the sort of dependence on the real part of the image coefficient, which actually changes sign and gives you this sort of attraction-repulsion effect. And if you actually do the calculations a bit further for a single polariton, you find that you have the polariton frequency here and the sort of Bose factor and this sort of signature of a near field effect. Okay, let me talk about my experiments. How do I do my experiments? So I do spectroscopic experiments that, in principle, I think they're very simple. What happens is, you take a vapor cell, it's got an atom inside, in vapor phase, and of course it's got windows. And what you do is you shine your laser beam and you measure the reflection from the window vapor interface. And if you go around the resonance of the atoms, you'll find that dispersion, the atomic dispersion, changes the refractive index and the reflectivity changes. And you can measure this signal. and you can actually sort of do a spectroscopy. Now, this naive approach is not entirely correct. It actually turns out that if you do the calculations properly, you find out that the transient response of the atoms that actually fly away from the wall plays an important role. So you actually get a sub-Doppler contribution, sort of narrow, high-resolution contribution of the atoms that come close to the surface, that fly kind of parallel here. And this allows you actually to measure the van der Waals interaction spectroscopically in a vapor cell. So, the calculations were done many years ago by Martial Duclois, and basically our protocol here is we do the experiment, we take a spectrum, we fit it to a theoretical model, and this gives us the C3 coefficient. This is the protocol. Okay, so the atom, I already told you, it was alkali atoms. This is the cesium atom. Some surfaces we use, usually the surface needs to be transparent. And I guess a criterion is that you need to sort of closely match the polarity and frequencies to the limit transition frequencies. Some of the materials we've considered is sapphire, is one of our favorites, with a polarity of 12 microns, and calcium fluoride, barren fluoride, 24 and 36 microns. This is a sort of graph of the image coefficient, real and imaginary part. You can see that sapphire, you actually kind of have to heat it up a lot in order to excite the modes, according to the Bose factor. Whereas these two, calcium fluoride and barren fluoride, they're a little bit easier to sort of handle. Nevertheless, one has to find good transitions, and if I show you here very briefly the sort of energy diagram of cesium, you'll see that this is the ground state. You'll see that you don't have these infrared wavelengths available if you start from the ground state. But of course, as you keep on going higher up, their levels are closely spaced together, and you can find them actually. You can find, for example, this one, the 8p level, that's coupled to the 7d level, at these wavelengths here, and you can do experiments with these dielectrics. Unfortunately, they don't work, and I don't have time to go into why. It's due to chemical instabilities, but you can sort of read about it if you like. But what I'll talk about is experiments that we did with sapphire, and these seem to be a little bit more successful. So, we actually probe this line, the 7D line, and in order to get there, we have to pass through the 6P, this is the D1 line, and then another laser, a red laser, to go up here. And why do we want to go here? It's because of this coupling at around 11 microns, which is relatively closely coupled to the polarity of sapphire at 12 microns. Now, as you can see here, this is a little bit far away, but I told you that the sort of surface resonances are not atomic resonances. And you can see here that you're a little bit far away. This is the atomic frequency, this is the polarity of sapphire, and you can still feel the effects here. Now, if you think about it, the surface, the polariton is red detuned compared to the atomic transition, so you would expect that if you heat up your system, then the atoms would like to feel more attraction towards the surface. And if you actually do the calculation, this is what you see. The C3 coefficient increases, therefore the attraction increases. But in order to see the effects, you need to heat it up to around, let's say, 1,000 degrees Kelvin. So this is a difficult experiment. I guess if you're an experimentalist, you can understand why. But it turns out that it is possible. You can actually find vapor cells. They're actually, the technology was actually made in the Soviet days in Armenia, and now it's the group of David Sarkisian that actually makes the cells for us. Special gluing, this is a very beautiful cell with a very nice sapphire window, like very low roughness, super polished window that's glued on a sort of tube, on a sapphire tube. And there's another window here, and there's this sort of cesium sidearm which controls the density. Now this part can be operated at 1,000 degrees Celsius, which allows us to do our experiments. So this is under vacuum, of course, now. And this part of the cell allows us to control the cesium density. Now we want to operate the cell at sort of high temperature gradient that allows us to sort of have vapor density that doesn't give huge broadenings and allows us to have some sensitivity in our measurements. Okay, so a little bit about the experiment. What we do is we have two lasers. we have a D1 laser at 894, which we lock to a saturated absorption setup, and then we AM modulate by a sort of boost optic modulator. This is the probe signal FM modulated, and actually the reflection is detecting a photodiode. You do a cascade lock-in detection, and the FM AM helps you to sort of get rid of all your noise that's not related to the atomic signal, whereas the FM stresses out, it takes the derivative and stresses out the narrow contributions. And this gives us basically this signal. So this is a spectrum. This is here the sort of cesium hyperfine structure. Here is the 3 lines actually involved. And I just show you some fits from the theoretical model that actually have to include 2 parameters. One is the C3 and the other one is the transition line width. So the blue line is the one that fits the best. It's a bit difficult, it's a highly nonlinear fit, so it's a bit difficult to sort of characterize the quality of the fit properly. So what I show you here, just to give you an idea of the error bars, I changed the C3 by 15%, and you can see that the curves don't fit very well. Obviously you can see that this sort of discrepancy is sort of concentrated in some hotspots mainly, but it is there, and it gives us an idea of our error bar, the error bar of our measurement. But we don't actually stop there. We actually do lots of tests in order to test that we're actually measuring something meaningful. One of the tests is that we're actually increasing the vapor density by increasing the temperature of the sidearm. This actually increases the line width, it changes the line shapes, but it doesn't change the C3. And when we actually fit, we find that we always have very consistent values of C3. Another thing we do is we actually change the hyperfine structure of components that we actually probe, and this also changes shape or the lines, but it never actually changes the numbers of C3. So we feel confident that we can measure the C3 coefficient with this technique, and we do actually this experiment at many, many temperatures. We start from around, let's say, 500 K, and we go up to 1,000 or even more degrees Kelvin. And this is how the spectra looks like if I take the 2 extremes. So you have the blue line, which is at 500 K, with a fit there that you cannot actually probably distinguish. And there's the red line that about 1,000 K. So this is a sort of, so you can notice that the red line is kind of shifted towards the red, which is a sort of typical of a stronger C3 coefficient. And it's also inhomogeneously broadened towards the red, another sort of typical sort of example. And if you look at the C3 coefficients, you'll find that they are indeed different, and they seem to increase with temperature, which is good news. This is what we wanted to show. Just to convince you a little bit more that what we're doing is meaningful, I'm actually showing you what a prediction of what the spectrum would be if there was no atom surface interaction. And this is what the spectrum would be. So like the effects are kind of dramatic if you actually put in the C3, actually you don't. So it's a real measurement. Let's sort of summarize the results. These are results of many, many, many hours of measuring. It's a bit of a shame that it's only one slide, but here it is. So basically, this is a theory line that I showed you before, and here are the experimental points that fit very well. Obviously, theory here is a little bit of a sort of relative term, because there are many things that are actually measured, and one of the things that is measured is the dielectric constant of sapphire in all frequencies, kind of hard measurement. And also, like, there are transition probabilities of cesium at some weird transitions that are not necessarily very well known. This is kind of a conservative sort of estimate of the error bars in theory. But in any case, there seems to be a very good agreement between the two. So we published these results like now a few years ago, but we didn't stop, and I'll go ahead and tell you some new experiments that we started since. I mean, they're pretty similar in nature, so you have to bear with me with those cesium energy level diagrams. I know you don't like them. So basically, we probed the second resonance of cesium at 7p. And why do we do that? Well, we do that for two reasons. First, there's a fine structure here, of course, 1/2 and 3/2. And one of the levels is very resonant with the sapphire, whereas the other one, it isn't. Okay? Or in fact, those two actually fall on the opposite sides of the sapphire resonance. So if I actually do the experiment, I would expect this line, the C3 of this line, to actually increase with temperature, whereas the other one would decrease and maybe even go down to 0. So I can have a sort of temperature where C3 goes down to 0. This is nice. Also, I can show some effects of absorption, or let's say near field energy transfer to atoms from the polarity modes to this sort of line, 7p69, which would also be very interesting, kind of analogous of near field heat transfer, but with atoms. And these are the experiments. I'll spare you the experimental sort of spectra this time. I'm sure I convinced you that we know what we're doing. So here you can see that the theory, the error line, the error bar in theory is huge due to different measurements in the sort of dielectric constant. Nevertheless, you can see that the 7p 1/2 line increases, and it's sort of kind of within the sort of bounds of these two measurements of the dielectric constant, which is very nice. And in the same scale, the 7p 3/2 doesn't increase, but unfortunately, it doesn't go down to 0. It sort of slightly decreases, but doesn't go down to 0, despite the theoretical predictions that actually wanted to. So we don't know exactly what's going on there, and what we're actually doing is we're performing our own measurements of sapphire resonances. We haven't analyzed them yet, but what you can see is that you have effects of temperature. Temperature actually changes the dielectric constant of sapphire, and therefore changes the polarity resonances, and these things have to be taken into consideration. So this is where we're at now. As far as sort of energy transfer, I'll just show you here, just to show you this. The energy transfer I'm talking about, it takes place at finite temperature, so this is a gamma rate associated with this transition, 7p6d. I just plotted here as a function of distance, and you'll see like the dramatic effects of the near field. This is log scale, and this is more or less the black body near the far field black body radiation expectations, with a sort of slight oscillation that I don't think we'll ever get to measure. But okay, what's going on here is that the near field is sort of very, very strong, and what you need is it's a very good method to measure it. So far what we're trying to do is we actually think that the information for the near field is actually embedded on the spectrum. So the spectrum actually carries information on the shift, but also on the gamma. And with proper analysis, maybe the data is actually there. Maybe we got it, but we need to analyze it properly. Anyway, very, very quickly, just changing subjects, just to sort of give you this preview, where we want to use this technique to actually study molecules instead of atoms this time. This is a very different experiment. Well, I guess I don't have to convince you why it's important, since most of you have written theoretical proposals here. There are nice things that can happen with molecules. Molecules have a complex geometry, they have chirality, they have anisotropy. They're important for physical chemistry, and they're not so much studied with sort of precision spectroscopic measurements. So this is what we'd like to do. Of course, they're not studied because they're difficult to study. So they have very weak transitions, and they actually have a sort of very complicated sort of row vibrational structure, which means that your partition function doesn't allow you to grow all of them. But in principle, selective reflection can do it. It's a sort of good technology. And we're trying it. So the first thing we're trying is SF6 molecules, simply because they give good signals. And we're going at 10 microns, very far infrared wavelengths. And thanks to Sean Tokunaga and Benoit Dartier, who are metrologists with molecules, we use their setup, and we actually managed to get some signals on the sort of row vibrational line. We would get some selective refractive signals. They are very weak. We have to average for many hours in order to get them, but they are there. And we're actually now building a new experiment with a QCL, sort of a nice sort of laser diode analog at sort of far infrared wavelengths, that we're very sort of hopeful, very I'm optimistic that it will give us some results. And of course, that'll be it. I guess we'll have to acknowledge the group that I'm working with. Daniel Bloch, Isabelle Morin, Marcel Duclois, João Carlos d'Aquino Carvalho, who is the PhD student, and Pedro Chaves de Souza Segundo, both of them from João Pessoa, or maybe Recife, I don't remember. And the guys that work with molecules, well, Benoît Darquier and Jean-Tom Braga, and the new student, Leon Bruce. Thank you very much.
Thank you. So we have time for questions. Yeah.
If you were to estimate the width of this 7p60 line, 7p 1/260, what would be the accuracy?
So the width of the, so it's a little bit complicated. So the transition probability is about, I think is maybe kilohertz, like a few kilohertz. But if you actually do a spectroscopic experiment, you'd be limited also, actually, you'd be limited by the finite lifetime of the state. So the transition probabilities here might be very small, so you might think that it's very accurate, but you have a finite lifetime here, which would actually limit the bandwidth to megahertz second, or sub-megahertz.
No questions?
Just a nomenclature question. These polaritons you're talking about, are they non-radiative surface plasmons in another language?
Yeah, I think so. I mean, it's a sort of.
That's what I know them as. The frequency is the root of epsilon equals -1, right?
The frequency is the root of epsilon.
It equals -1. So the denominator epsilon plus 1 vanishes.
Yes, that's it.
So that's the same thing. Thank you.
Any further questions? Yes, Francesco, as always.
Sorry.
Thank God there is Francesco.
So I have a question which is mostly probably a dream of a theoretician.
Okay.
So I was wondering, and something that I've wondered since a while, and probably the answer is no, but I prefer to ask. Is there a way to selectively excite or thermally excite surface plasmons alone? Only the surface plasmons without touching to the other modes of the system? Experimentally, of course. Theoretical is.
I think yes. I think.
I think
So yeah.
Greetings.
People can.
so. All right. Why not?
I think people do surface plasmon resonance as well, where you have a thin layer of gold and you reflect from one side of it and you excite the plasmon on the other side.
Sure.
And that has a longer range. And then you're using the same laser to excite the modes and to measure, and you look at a change in the reflectivity.
Just a reminder here, we're not using any lasers. Right? These things are thermally excited. We're just heat it up. So I think if you heat up the whole system, then you unavoidably heat all the modes. But I think if you just heat the temperature, so if you go into an out of equilibrium thing, if you heat the surface, then I think you'd be mostly addressing the evanescent modes and not, well, okay, it's not sure because it will radiate, huh? But, well, I cannot think of any other way just to selectively excite. Maybe the laser would be a good idea.
Yeah, so I think what you can do is, if you've got you can sort of vary the plasmon frequency by varying the thickness of gold layer, and then you change the angle of your laser, and there's a certain angle where you excite the plasmon with the resonance.
This is as a drawback, but yeah, okay, yes.
And then people do actually use that to then measure sort of molecules on the surface. They could use that to measure. But it's all that will be at optical frequency, so I don't know if that's any use.
Yeah.
I guess this doesn't really answer your question.
Not completely, because actually it's more related to the full dispersion relation of the surface plasma. This is not only one particular value,
Yes,
Okay.
I know, like the lasers tend to actually put photons in one.
Exactly.
mode.
This is actually one of the drawbacks.
Yes, but other than a sort of out of thermal equilibrium sort of situation, but as you say, it's not clear to me. Why would you want to do it? You'll tell me afterwards.
Okay, any further questions? If this is not the case, then we thank Athanasios again.